All right, good morning, gang. Welcome back. Today we are going to talk some more about polynomials, of course. We're going to stay on that track for a little bit. Your tests are not graded yet. I am hoping to get them graded today. By the end of the day, that is my goal. Yeah, function of how much time I have available. We will see. I'll do my best to get all your free response scores in today. All righty. I may turn off that baby monitor just to spare you guys the noise. But yeah, let's go ahead and do this thing first. So this is MAC1140, section 008, which means we're talking pre-calculus. And today is the 30th of September 2021. And the plan for today is to talk about more polynomials. We're going to finish 3.2. And maybe we'll get into 3.3. We'll see. So the homework that I opened up for you guys on Tuesday, I set that to be due next Tuesday because I just want to make sure everybody has plenty of time. I was a little bit late getting it up. So don't panic that it wasn't due today, but do try to get it done as quickly as you can. Because the material that we're going to be talking about today kind of builds on that. So last time, I recall, a polynomial of degree n, and n here is an integer and it's not negative, is an expression of the form. We usually use the symbol p of x, right? It's a function, it's a polynomial, and the variable is x. Call it p of x. The largest power of x is x to the n. And there's a number multiplying that x to the n, which we call an. You remember this, we went through this last time. And then an minus 1 times x to the n minus 1, and we go down like this until you get to a linear term and then a constant term. Right, so anything that can be written this way is a polynomial. N is a non-negative integer. So all the powers of x are non-negative integers. The an minus 1, all these things, all those a's are constants. Called coefficients. An itself, which should not be 0, is called the lead coefficient. All right, so I just wanted to remind you the definitions and the sort of basic bits of terminology surrounding polynomials. Moving forward from here, we're going to talk about graphs of polynomials, how factors affect the shape of the graph, local behavior near roots, all sorts of good shit like that. Before we do any of that, though, I just want to look at some things and ask, is this a polynomial? Is this not a polynomial? If it is a polynomial, can we talk about the coefficients? Can I label those things to make sure that everybody's comfy with the definition here? Because I know it's maybe a little bit intimidating looking the first few times you see it. So, some examples, right? If I have something like doesn't matter, p of x equals negative 5x to the 4 plus 6x cubed minus 2x squared plus 3x plus 7. This would be a polynomial of degree 4. I'll state the coefficients. So the degree of this guy, the largest power of x that shows up anywhere, is x to the 4. So we would call this a degree 4 polynomial. And then those coefficients, I would call this guy A4, this guy A3, this guy A2, this guy A1, and this guy A0. So the lead coefficient, A4, is -5. The cubic coefficient, or degree 3 coefficient, is 6. The quadratic coefficient, A2, is -2. A1 is 3. And A0 is +7. So nothing too complicated about this. I know this thing looks scary, right, in general, but in practice, these are not that scary. It's just that we don't know how many of these things there are. That's the only reason the formula looks frightening. There's going to be another homework coming out today, and it's also going to be due on Tuesday of next week. All right. So like we said, the big guy up front here, the coefficient attached to the largest power of x, we call the lead coefficient. And he turns out to be pretty important for this thing called end behavior. So the homework that you have up right now has you graphing just straight power functions like x, x squared, x cubed, x to the 4, x to the 5, and so on. I'm not going to go back over those. I trust that you guys remember those. We've been using them as parent functions all semester. But we haven't talked is this concept of end behavior. So I do want to talk about that. Oh yeah, and before that, some facts about polynomials. So polynomials are continuous functions. Continuous everywhere. And what that means is that their graphs are connected or unbroken. Two, polynomials are smooth. Which means their graphs don't have any sharp points. Which are also sometimes called cusps. Let's see, is there anything else we really want to say? No. I'll finish up here by saying every polynomial exhibits one of the following. We call end behaviors. So end behavior is how the function behaves for very, very large values of x, either very large positive values of x or very large negative values of x. In terms of the graph, end behavior tells you whether your arrows sort of at the end of the portion of the graph that you draw should point up on both sides or down on both sides or up on one side and down on the other. That is what we mean by end behavior. And I'll show you some examples here. So in other words, no polynomials don't have any asymptotes. Don't have any horizontal asymptotes or vertical asymptotes. Well, if you've heard those terms before, they exhibit a particular kind of end behavior. So you know it's possible for a polynomial, something like x squared, to have end behavior like this. But not just x squared, there's lots of things that could exhibit end behavior like that. So when we talk about end behavior again, we're just talking about these arrows. I don't care about what goes on in between. That's why I've drawn that as like dashed. Just talking about the arrows. It's also possible that the arrows point down. On both sides. All right, this could be the graph of a polynomial. And then you think of like the graph of x cubed. So there are end behaviors like these, where it goes down on one side and up on the other. And then there's kind of the flipped over version of that, where it's up on the left and down on the right. So each one of these little graphs here, tiny little graphs, exhibits a certain kind of polynomial end behavior. And that end behavior is going to be really helpful for us when it comes to sketching graphs. So kind of our goal here in chapter 3 is to get to a place where I can give you a polynomial, a big one, like degree 3 or 4, and you can, through some process, draw a really nice graph. One of the most important things, one of the most useful starting places there is the end behavior, and it's very easy to figure out. So check this out. In order for a polynomial to exhibit end behavior like this, where the arrows point up on both sides, this means you have a, I'll do the degree first. The degree is even, like 2, 4, 6, 8, even degree, and positive lead coefficient. So any polynomial that has an even degree and a positive lead coefficient will have end behavior like this, meaning the arrows on both sides go up. This fella corresponds to a polynomial of even degree, but a negative lead coefficient. I think like negative x squared, right? Obviously the in-between part looks very different, but just negative x squared would have arrows that point down on both sides. This fella is an odd degree and positive lead coefficient. I just realized I have the opportunity to embarrass myself for you again today. It's a good section for that. And then the last one here is odd degree negative lead coefficient. So kind of the long-term goal here, like I said, is to graph polynomials. I give you a polynomial graph. The first thing you're going to do is look at the end behavior. Then you would factor and find the roots and find the local behavior near the roots. And I'll show you how to do all that stuff down the road. But the very first thing you need to do is find the end behavior, because this is going to tell you kind of how to start drawing your graph. I mentioned that this is an opportunity to embarrass ourselves, and embarrassment is always a good way to help us remember shit. So right, it works better in person. I usually stand in front of each one of these and do my arms like that. It will, the end behavior dance, right? So if you like, you can think of these as coming from a goofy little dance. You think of these as like arms. If you don't want to think of it that way, that's totally fine. I understand. So let's see if we can detect the end behavior of some polynomials. And then we're going to talk a little bit about factors. Oh, the notation. I have to show you the notation. I'm so sorry. There's a special notation that goes with each of these. It's called the goes to or arrow notation. So to describe this behavior, the arrow going up on the left, I would say as x goes this way, y goes this way. Now, really, really far out this way is as x goes to negative infinity. And we would say as x goes to negative infinity, y goes to positive infinity, because the y values are going up as the x values go off to the left. To describe this arrow over here, I would say as x goes to positive infinity, y goes to positive infinity. For this guy, I would say as x goes to negative infinity, y goes to negative infinity, because as we go to the left, we go down. And this guy over here, I would say as x goes to positive infinity, y goes to negative infinity. So it's all infinities, right? And then you just have to choose the sign that makes sense. So somebody tell me, what would be the arrow notation, the like goes to notation for this arrow here to describe a polynomial which goes down as you go out to the left? Okay, we can do this one together. So here we're wandering out to the left, and as we go really far to the left, the arrow points down. So we'd say as x goes to negative infinity, right? This means we're going far off to the left. Y goes to negative infinity. That means we're going down. This guy. So with that in mind, how would I describe this one or this one? Let's do this one first, just to make. Okay.
As x goes to negative infinity, y goes towards infinity.
Yeah, very good. That's perfect. What Timothy said there was perfect. As x goes to negative infinity, as I wander really far to the left, y goes to positive infinity. The y values are going up. All right. This goes to or arrow notation is going to be another useful thing as we develop our theory of polynomials and rational functions. All right, let's see if we can detect the end behavior. For a polynomial and describe it in that arrow notation. So state and draw the end behavior. Well, let's do a couple guys here. How about p of x equals negative 2x to the 4 plus 5x cubed minus 7x. And call this other guy q of x, why not? Cubed plus 4x squared plus 4x plus 1. So what do I need to identify to find each of the end behaviors here that I'm asking for?
The degree and lead coefficient.
Very good. Yeah, we need the degree. So, and the lead coefficient. All right, so in part A here, what is the degree? What's the degree of this polynomial?
4.
What is 4?
Yeah, good, it's 4. And the lead coefficient?
-2.
Good. So the degree is 4, which is even, and the lead coefficient is -2, which is negative. So let's draw the end behavior here, and then we can try to describe it in the arrow notation. Even degree means the arrows are going to go the same way. They're both of them going up or both of them going down. And the negative lead coefficient means that they got to both be going down. All right, so that's those 4 cases. And I have no idea what the hell else is going on here. This thing could look like a whole basket of crazy in between. I don't know, but I do know it has those sort of end behavior arrows. And then if I wanted to describe this in the goes to notation, there's kind of 2 ways that those start. As x goes to -infinity, y goes to somewhere, and as x goes to +infinity, y goes to somewhere. Sorry, I have something in my throat. I'll be right back. Okay, so for this polynomial, as x goes to -infinity, where is y going?
Y also goes to -infinity.
Yeah, also going to -infinity. As we go to the left, we're going down. And as x goes to +infinity, we're also going down. So y would go to -infinity there as well. Q of x here, the degree is 3, which is odd. And the lead coefficient is what? What is the lead coefficient here?
1.
Very good. Yeah, remember, if there's nothing written there, it's a 1, which is positive. So this guy, odd degree, so the arrows point different directions, positive lead coefficient. So the arrow on the left goes down, the arrow on the right goes up. And again, I have no idea what the hell this thing does between those two. All I know is it has that sort of end behavior. And this guy would be as x goes to -infinity, y goes to -infinity. And this would say as x goes to +infinity, y goes to +infinity. Okay. So determining the end behavior is not too hard. If you want to cook up a nice graph, you need the end behavior and you need to know the x-intercepts. It turns out that's enough. If you know the x-intercepts and specifically the factors that they're coming from, then we can use that together with the end behavior to draw a nice graph. So let me give you a theorem here. Let P be a polynomial C be a real number. This is another TFAE. The following are equivalent. One. X equals C is a root, or I should say of the polynomial p of x. And remember, root is just another word for 0 or solution to p of x equals 0 or x-intercept. This is equivalent to saying x equals c is a solution to the equation p of x equals 0. Nothing exciting there. Definitely more exciting than that first implication is that x minus c, if c is a root, is automatically a factor. All right, in other words, p of x can be written as x minus c times some other polynomial of degree 1 less than p. So factors tell us roots, and roots tell us factors. If you know one, then you know the other. And then roots are the same thing as solutions to this equation. To graph a polynomial, you want to find all of the roots. You want to find all of the x-intercepts. You want to find the end behavior. And then generally you want to maybe plot a few extra points. However, there's more to the behavior near the roots that we can use to really help us draw a nice graph. And this is called local behavior. I apologize if I'm not my normal chipper self this morning. I very, very low on sleep. Had a difficult night, so I'll try and hang in there for you. But local behavior near roots for polynomials. All right. The multiplicity of the root is what tells us how the thing will behave. So first, suppose x minus c to the m is a factor of the polynomial p of x. This means, when you factor p all the way, this term like x minus 2 or x minus 5 or whatever shows up with a certain power. This power is called the multiplicity. And I'm assuming that p is totally factored. In other words, that there aren't any other copies of x minus c that we could still factor out. The parity of m, the even or oddness of this multiplicity, tells you how the graph behaves near that x-intercept. So what I'm going to do over here is state the multiplicity, and over here I'm going to sketch the behavior near the root. This is probably the easiest way to convey the theorem. So if the multiplicity is 1, then near that root, whatever here's c, my polynomial is just going to cross over the x-axis. All right, and I have no idea what's happening elsewhere. I don't particularly care. That's just the local behavior. if m is equal to 2, then the local behavior there is going to be something like this. It's going to bounce off the x-axis rather than crossing over it, right? And I guess we should say there's other ways it could cross over, right? It could also cross over like this, and you could also bounce like this. If m is equal to 3, if you have a multiplicity 3 root, then the behavior near that root is going to be similar to the behavior of x cubed near 0. Something like this, and so on. All right, if m is equal to 4, I don't think we'll ever deal with any multiplicity 4 roots, but then the local behavior near that guy is going to look like x to the 4 looks near 0. So kind of, this is the idea, right? Is that the multiplicity of the factor, the power of the factor, the multiplicity of the root, kind of makes the graph of the polynomial look like the simplest version of a function with that multiplicity. In particular, I'd like you to notice that odd multiplicities, you cross the x-axis. That's a big deal. It means you change sign. P of x changes from negative to positive or positive to negative as you jump over that root. And even multiplicities you don't. This idea, local behavior near roots, together with the end behavior of the polynomial, really is enough to graph the thing and graph it well. Let me show you what I mean. Maybe I should say, you know, this and let's leave it at this. Okay. So for example, sketch the graph of P of x equals x cubed times x plus 3 squared times x minus 4. Okay. What is the degree of this polynomial? And think carefully, think carefully.
Would it be 3?
So 3 is a tempting answer, right? Because it's the largest power of x I see anywhere here. But this is not in that form of a polynomial, right? This isn't like some constant times x cubed plus some constant times. I've got this multiplication. This is in what's called the factored form. So you have to imagine sort of multiplying all of these out and then ask what would be the largest power of x then?
Would it be 6?
Yes, yes, the degree here is 6. Which is even. And again, if you imagine multiplying all of this out, what would be the lead coefficient? I know it's not easy to see, but I think you can get there.
Would it be 1?
It would be 1. Yeah. Why would it be 1? That's correct. I'd like to pick your brain a little bit. How can we tell?
Because it would
When you
be
multiply-
like when you multiply the x times the x.
Yeah, that's really what's going on here, right? So if I FOIL this out, the x plus 3 squared, the first term is going to be like the highest order term there is going to be x squared, 1x squared. If I multiply that by 1x cubed, I get 1x to the 5th. And then when I multiply that by this 1x, I get 1x to the 6th. So you can tell that if I were to multiply this out, the very first term would be 1x to the 6th. A trick for the multiplicity or for the degree. The degree is always the sum of the multiplicities. Not that you necessarily need to memorize it like that, because you can always just imagine multiplying all this stuff out. But kind of faster way to do it is just the sum of the multiplicities. So here's a multiplicity 3 factor, here's a multiplicity 2 factor, and here's a multiplicity 1 factor. 3 plus 2 plus 1 is 6. So that can be a useful tool. And then the lead coefficient, you just have to imagine what's the lead term from each of these pieces. X cubed, x squared, x, all with a 1. So 1x to the 6, which means my end behavior is what? I've got an even degree and a positive lead coefficient. So as x goes to negative infinity, y goes to positive infinity, and as x goes to positive infinity, y goes to positive infinity. In other words, I can begin drawing my graph with arrows going up on both sides. I don't know what the hell else is going on, but I know it's got these arrows going up on both sides. The next thing I need to do is say, what are the x-intercepts, or what are the roots? Anybody tell me one of the roots?
Would it be positive 4?
Mm-hmm.
And -3.
Good. 4 and -2. There's another one.
Zero?
Yeah, 0. X cubed is x minus 0 cubed. Might be useful to think of this. That factor x cubed
Shouldn't it be
is x minus 0 all cubed.
-3 instead of -2?
Oh, I wrote -3. Yeah, sorry, -3. Yes, -3. Okay, and what is the multiplicity of each of these roots? What's the multiplicity of the root at 4? Coming from this factor.
1.
Yeah, 1. It's the power of the factor, right? What is the multiplicity of the root at -3?
2.
2,
Yeah, it's 2, because that's coming from this factor. And the multiplicity of the root at 0 would be
3,
very good. All right, so here's what we do. We take these roots and we plot them, right? One of them is here at 0. One of them is over here at -3. I'll just call this -3. And one of them is over here at 4, right? I'll just call this 4. Now, this is why you need the end behavior and the local behavior near the roots. Watch what I'm about to do. I know because my end behavior is up on the left that the graph has to come in like this, right? And it has to touch the x-axis here. Am I going to cross over the x-axis, or am I going to bounce off of the x-axis at -3?
Say bounce.
It's going to bounce, right? Because the multiplicity at -3, the multiplicity of that root is 2. Now it's possible to bounce bottom to bottom or top to top. What's going to happen here? Are we bouncing top to top or bottom to bottom? Am I going to do, or am I going to do? The key is this thing. I know I have to come in from above because I know my end
Be top
behavior.
to bottom.
Yeah, it has to be a top to top. Has to be a top to top because it's got to be a bounce. And I need to connect to this thing. Right? So I can't bounce bottom to bottom here because I don't have another x-intercept. I need to get to this arrow. And this is my leftmost x-intercept. So I have to go straight from this arrow to that x-intercept. All right. Now I've got also this root here at 0, which is multiplicity 3. He's going to have local behavior looking like this. He could do either this or this. Could go up to down or down to up based on the multiplicity. But because I know I'm leaving this root at -3 by bouncing up, I have to come back to this guy from above. And then the root at 4 is multiplicity 1, so he's just going to be a straight cross. He could go like this from bottom to top, or like this from top to bottom. Which one's going to happen here based on the way we leave the origin? Are we going to come through 4 like this? Or am I going to come through 4 like this?
Bottom to top.
Bottom to top, good. Because I have to be arriving from below, because I'm below here. And now you just put these pieces together. There's your graph. Now, I haven't drawn any scale for the y-axis because I don't have a goddamn clue. This hill right here might be really tall, or it might be really short. Similarly, this valley right here, it might go way down, or it might just go down a little bit. But I want to draw your attention to the fact that this thing has the right shape. It's not just that it's got the right roots. It's not just that it goes from positive to positive or positive to negative or negative to positive at the right places, but it has, like, whatever the correct graph is, it has to have a max over here because we have to be smooth and connected, and we have to go from increasing here to decreasing here in order to get back to 0. So really quick, let me show you what this polynomial, which I totally just made up, looks like in Desmos, and we'll see how close we were. X cubed times x plus 3 squared times x minus 4. All right, I'm going to zoom out a little bit. I'm going to fuck up this y scale a little bit. Yeah, negative 500. Yeah, it's going way down there. I'll just leave it like this. All right. So you see here, that shape, our shape, that shape, our shape, that shape, our shape. We nailed it, man. Like I said, I don't know how tall this hill is. I don't know how deep this valley is. Turns out this valley is super duper deep. This hill is not super duper tall. The hill is like going up to a height of 50-ish, and the valley is going way down there, like negative thousands. Yeah. But this is a really good picture, right? And in particular, it has the right number of mins and maxes. I've got 1, 2 mins, and 1 max. 1, 2 mins, and 1 max. So our guy really has the right shape in a very meaningful way, which is a big deal. And this wasn't very hard to get. All I needed was the end behavior and the roots with their multiplicities to draw this graph. And if you want to make this graph really, really good, you would plug in a few x values, like between -3 and 0 to figure out how tall this hill is or get an idea. Plug in a few x values between 0 and 4 to figure out how deep this valley is. And you could have yourself a perfect looking graph. And I think that's pretty impressive. I think given how much we've leaned on graphing calculators in the past, that we can do this on our own by hand is really quite beautiful. Okay, this I think is all we have time for today, right? Yeah, 11:44. I'm gonna go ahead and end the meeting here. This is the big goal in 3.2, is to get you guys to a place where you can draw these graphs. The challenge, the real challenge in fucking around with polynomials is getting the polynomial into this form, right? Factoring it. If I gave you the multiplied out version of this polynomial, factoring it like this is gonna be tricky. So the remaining sections here in chapter 3, we're talking about polynomials, will have to do with factoring tricks, synthetic division, dividing polynomials, all sorts of good stuff. But I'm not going to dump that on you just yet. So for now, focus on, taking a polynomial like this, getting a nice graph, detecting whether a graph could or could not be that of a polynomial, or taking a graph like this and possibly giving the factored form of the polynomial. All of those are very important skills, and that's what I'm going to dump into your homework today. On Tuesday of next week, I'll start talking about how to divide polynomials and all of the little tricks we have for factoring big ass polynomials like these. All right. Papers or tests should be graded later today. That's my goal, is to get all your stuff in there later today. So watch for that. It will show up in Canvas. And that's it. Take care.